Welcome to Lecture 1 of Physics 506. This first lecture is going to be a review of spin and Pali matrices. I'm going to go through the material fairly quickly because this is material that you should know. However, as I mentioned in the introductory video, you should watch this video, pause it, take notes while you're watching it. And then I even recommend that you watch it a second time, perhaps a day or two later, perhaps at a slightly faster speed, just so that you are clear that you understand all of the concepts that are being presented in the material. So to start, we're going to recall that the spin operators and eigenstates satisfy the following relationships. We're going to call the z component of spin sz. We're going to call the eigenstates up and down with a semicolon to say what axis the up and down are on. And then the eigenstate relations are that sz acting on the up state is equal to h bar over 2 times the up state, and sc acting on the down state is minus h bar over 2 times the down state. That indicates that they're eigenstates. Now we also define raising and lowering operators, s plus and s minus, that connect these two states. So s plus acting on the up state is equal to 0. It annihilates that state because I can't raise it any further. S plus acting on the down state converts it to the up state and multiplies it by a factor of h bar because that's the units of the spin operator. So s plus acting on down equals h bar times up. Similarly, s minus acting on up equals h bar times down, and s minus acting on down is equal to 0. Now we can use these definitions on these states because the set up z and down z is a complete set or a complete basis in this two-dimensional space that we're working in. So then if we look at s plus, s minus, minus, s minus, s plus, let's look at the first term. S minus acting on up, that's going to give me h bar times down, and then s plus acting on down gives me another h bar times up, so that's going to give me an h bar squared times up, whereas the second term, s minus s plus acting on up, the s plus acting on up annihilates it, so that gives 0, and I'm left just with the h bar squared times the up, and I can rewrite that as 2 times h bar times sz. Similarly, if I look at s plus s minus minus s minus s plus acting on down, the first term is trying to lower down, that gives 0. The second term with the minus sign first raises the down to up. I get h bar times up, and then it will lower that up to down with another factor of h bar, so we get a net of minus h bar squared times down. And again, that is also 2h bar times sz acting on down, because when sz acts on down, I get minus h bar over 2. And we learned from this that the commutator between s plus and s minus is 2h bar sz. And I want to really make it clear to you that this really is a derivation of that commutator by acting on the states, because those states form a complete basis of the space that we're working in. Now you can do a similar calculation using sz and s plus, and note that sz, the commutator of sz with s plus acting on the up state, is going to annihilate it. It's going to give 0 because I always have an s plus, which annihilates the up state. And acting on the down state, it's going to give me a h bar squared up, because each term gives an h bar squared over 2 times the up state. And we can think of that as being h bar times s plus acting on, that should be acting on the down state. That's a typo there. And so what we find is that the commutator of sz with s plus is h bar times s plus. And using this exact same technique, you can verify that the commutator of sc with s minus is minus h bar s minus. So these three commutation relations, which might be a little bit unfamiliar to you than the conventional angular momentum commutation relations, actually are the SU2 algebra expressed in terms of raising, lowering, and z operators. And then from this algebra, we can define an Sx as 1/2 S plus plus S minus, and an Sy as 1 over 2I S plus minus S minus. We then have the inverse relations, which write S plus as Sx plus ISy, and S minus as Sx minus ISy. And then you can figure out that the algebra of the Cartesian operators then simply follows as the commutator of Sx with Sy. We just plug in the definitions. Sx is 1/2 S plus plus S minus. Sy is 1/2I S plus minus S minus. We have the commutation relations between S plus and S minus. Commutations of S plus with itself and S minus with itself are, of course, 0. S plus with S minus gives 2 H bar Sz. And you see when all the dust settles, you get I H bar times Sz. And then you should verify, if you then look at the other possible combinations, that the commutator of Si with Sj is IH bar sum over k, epsilon ijk sk, where epsilon ijk is the completely antisymmetric tensor. When I have an even permutation of 1, 2, 3, the epsilon is equal to 1. When I have an odd permutation, it's equal to -1. And if any of the indices are the same, it's equal to 0. Now, that's something that you really should be familiar with, but I'm showing you here an alternative way in which you get it by working with the operators and the definitions of how the operators act on the states. Okay, we also can now work out what the commutator of S squared with Sj is. It's equal to 0, and we're going to just prove it by using the Leibniz rule for the commutators. So first we write out that S squared is the sum over I, Si, Si. Then the commutator of S squared with Sj is the sum over I, Si, Si commutator with Sj. We then use the Leibniz rule, which pulls an Si out to the left and an Si out to the right. And you get a sum over I, Si commutator of Si with Sj plus Si commutator Sj with Si. Now, we know what the commutator of Si with Sj is, so we just plug that in. It's epsilon ijk sk with a sum over k. So we now have the sum over I and k of epsilon ijk Si sk plus sk Si. Now, our claim is that that is equal to 0. To see this, let I go to k prime and k go to I prime. So then I'm going to have that series on the top. It's going to be rewritten as sum over I prime k prime, epsilon k prime j I prime sk prime, Si prime plus Si prime sk prime. That is simply a relabeling of dummy indices. Please be sure you understand that that doesn't change anything. It's just a way of expressing the exact same thing. If you have any trouble with understanding that, pick a particular value of j, work out the summations on those two lines, and verify that they really are the same. Now what we're going to do is we're going to interchange I prime with k prime. When I interchange two indices in epsilon, in the antisymmetric tensor epsilon, it gives me a minus sign. So I can rewrite that epsilon as minus epsilon I prime j k prime. And then what I'm going to do is I'm going to take the second term in the summation and move it to the first term, and take the first term in the summation and move it to the second term. So that I'll get Si prime sk prime plus sk prime Si prime. Because addition is commutative, that's obviously something that I can do. And now what we're going to do is we just drop the primes. They're dummy indices after all, so I'm going to get minus IH bar sum over IK epsilon IJK Si SK plus SK SI. You can see that's the opposite of the thing that we started from. That means that this function is equal to minus itself. Now, the only thing that's equal to its negative is 0. So that means that S squared commutator with Sj is equal to 0. All right, so let's compute what S squared is when it acts on one of these states, where sigma is equal to up or down. S squared is equal to Sx squared plus Sy squared plus Az squared, but we want to express it in terms of S plus and S minus because it's much easier to work with S plus and S minus when I'm working with states that are in the eigenstates in the z direction. So I substitute in for Sx as 1/2 S plus plus S minus, and that quantity is squared. I substitute in for Sy with 1/2I, S plus minus S minus, and that whole thing is squared, and then plus Sz squared. Now, we work out the terms. You see I'm going to have a 1/4 S plus squared, but I'm going to have a minus 1/4 S plus squared. Those terms will cancel. Only the cross terms survive, and they're the same, and I have two of them. So the net effect is I get 2/4, or a 1/2 times an S plus S minus plus S minus S plus Sc squared. This is a very useful relationship for S squared. It's one that you should remember. Now we can just apply this onto the state. Let's apply it onto the up state. The sz squared term is easy to evaluate because sz acting on that state gives me h bar over 2. If I do it twice, I get h bar over 2 quantity squared, so that's going to give me an h bar squared over 4. The first term, notice that the second term in the first term is an s plus, but s plus acting on up annihilates it, so that term is gone. The second term is an s minus s plus. You can see the s minus will multiply by h bar and take the up to down, and then the s plus will multiply by h bar and take the down to up. So the net is that I get an h bar squared over 2 from that first term. Add that with the 1/4 h bar squared from the third term, and you get a 3/4 h bar squared. Now you can do the same thing acting on the down state. In this case, the s plus s minus term is going to annihilate, but the s minus s plus term is going to give me an h bar squared over 2. And the sz squared term is the same because minus h bar over 2 quantity squared is still equal to h bar squared over 4. So you get 3/4 h bar squared for that state as well. So the states sigma semicolon z, or sigma along the z-axis, are eigenstates of both s squared and sz. Now, let's assume that we have an arbitrary superposition of states. So psi is equal to alpha times up plus beta times down. And we can often find it convenient to rewrite that as a vector using just the components in front of the kets, writing it as alpha beta to denote the state psi. The operators Si are then represented by two-dimensional vectors in this space. And the way that we figure out what those two-dimensional they're two-dimensional matrices in this space. And the way that we figure out what the matrices are corresponding to the operators is that we compute the components of that. So let's look at what happens when sz acts on up z. It gives me h bar over 2 times up z. And when it acts on down z, it gives me minus h bar over 2 times down z. Sorry, there's a small typo there as well. The minus sign got suppressed. That then is equivalent to the matrix h bar over 2 1, 0, 0, minus 1, because when I multiply that times 1, 0, I get h bar over 2 times 1, 0. It's an eigenstate with the right eigenvalue. And similarly, when it multiplies 0, 1, it gives me minus h bar over 2 times 0, 1, which is the correct eigenvalue. The other way that we can calculate it is we actually calculate the matrix element. There are 4 terms here because sigma can be up or down and sigma prime can be up or down, where we take the matrix elements with a bra sigma z si ket sigma prime z. Now, I find a lot of times people have trouble figuring out how to compute this. So let's just talk you through how that's done. For the sz, you can see you first operate the operator onto the state, onto the ket, and that's going to give you some result, which is going to be a linear superposition of kets. And then you just use the orthonormality of the kets and you multiply by bras each in turn and figure out what the coefficients are. And from that, you can get the matrix. So for example, the top row of the sz matrix, because sc acting on up is h bar over 2 times up. When I multiply that by the up bra, up with up, that overlap is equal to 1. So I get h bar over 2 in the first element, and then when I multiply it with the down state, because up is orthogonal to down, I'll get a 0. And you see that tells me that the first row is h bar over 2 times 1, 0. And you can similarly work it out for the next row. So now we're going to use this to calculate it for sy. And again, the strategy is to use the s plus and s minus because we know what those operators do to these different states. So I get 1 over 2i s plus minus s minus, and I have to sandwich it between the sigma and the sigma prime. And as I said, the first step is you operate the s plus minus s minus on the up state. That is going to give me minus h bar times the down state. Now I look at the different bras multiplying it. When I multiply it by an up bra, I get 0 because up and down are orthogonal. So the up element of sy is 0. When I multiply it by a down ket, I get I h bar over 2 because I have that 1 over 2i in front. And that's the down up element of y. And then similarly, you work it out for acting on the down state, and you'll get the up down and the down down elements of y, of sy. And that means that the sy matrix is h bar over 2, 0, minus I 0. And you just have to be careful about figuring out, remember, the top row corresponds to picking the bra to be up and then looking at different kets. And the bottom row corresponds to picking the bra to be down and looking at the two different kets. And then similarly, you can work out that Sx is h bar over 2, 0, 1, 1, 0. And we already worked out what SZ is. So we call these three matrices the Pali matrices. We have sigma x, sigma y, and sigma z. You can note by just squaring them that sigma squared, each of them squared is equal to the identity matrix. That means that S squared written as a matrix, taking the sigma sigma prime matrix of S squared, is going to give me h bar squared over 4 times the sum of 3 identity matrices. So I'll get 3 h bar squared over 4 times the identity matrix. You should think about what that means corresponding to the fact that the states up and down were both eigenstates of S squared with the same eigenvalue, 3h bar squared over 4. These matrices also anti-commute. Now, this is not quite so easy to see, but we're going to actually work it out by looking at our spin commutators. So let's start by looking at the commutation relation. Commutator of Sx with Sy is equal to IH bar Sz. Let's multiply that equation on the left by Sx and on the right by Sx. So I'm going to get two equations which are now written for you below. Sx squared Sy minus Sx Sy Sx equals IH bar Sx Sc, and Sx Sy Sx minus Sy Sx squared is equal to IH bar Sz Sx. We now substitute in the Pali matrices. Each S gets replaced by an h bar over 2 times a Pali matrix sigma. That's going to give me an overall factor of h bar squared over 8. H bar cubed over 8. And I'll get a sigma x squared sigma y minus sigma x sigma y sigma x equals I h bar cubed over 4 times sigma x sigma z. And then similarly for the second equation. And now what you can see is we're going to add these two equations together. You see, when I add these two equations together, on the right-hand side, I'm going to get the anti-commutator, sigma x sigma z plus sigma z sigma x. Looks just like a commutator, but it has a plus sign rather than a minus sign. And on the right-hand side, you see because sigma x squared is equal to 1, and because the triple product term cancels because it has opposite signs, you see I get a sigma y minus sigma y, which is equal to 0. And that tells me that sigma x sigma z anti-commutator is equal to 0. And then obviously you can see this is going to hold for the other permutations. So what we have learned from this is that sigma I sigma j can be written as 1/2 the anti-commutator, sigma I sigma j plus sigma j sigma I, plus sigma I sigma j minus sigma j sigma I. You see, all I did to this is I added 0. I added sigma j sigma I and I subtracted sigma j sigma I. But now we organize these in terms of the anti-commutator and the commutator. Now the anti-commutator is equal to 0 if I does not equal to j. But remember, when I equals j, the square of each Pali matrix is equal to 1. And then when I sum two of them together, I'll get twice the identity matrix. That factor of 2 will cancel the 1/2, so I'll get a delta ij times the identity matrix. And then the anti-commutator, when I look at the Pauli spin matrices, the anti-commutator is 2I epsilon ijk sigma k with a sum over k there. And so the 2 and the 1/2 cancel, and I get I epsilon ijk sigma k. Now, this is a really important identity. The product of two Pauli matrices, sigma I sigma j, is delta ij times the identity matrix plus I epsilon ijk times sigma k. Now, another interesting identity is the product of all three of these. Sigma x, sigma y, sigma z. Using this identity that we have above here, I'll just move it down so you can see it. If I look at sigma x times sigma y, that equals IH bar epsilon 1, 2, 3 sigma z. And then sigma z times sigma z is equal to the identity matrix. Epsilon 1, 2, 3 is equal to 1. So you see it's equal to IH bar times the identity matrix. I'm sorry, there's no H bar in there. Sorry, knock that H bar out. That's a typo as well. And so you get sigma x, sigma y, sigma z equals I times the identity matrix. Now, any 2x2 matrix can be expressed in terms of the identity and the three Pauli matrices. So let's check that. Let's look at alpha times the identity matrix plus beta times sigma x plus gamma times sigma y plus delta times sigma z. I'm going to get alpha plus delta, beta minus I gamma, beta plus I gamma, and alpha minus delta. To re-express this in terms of any matrix A, B, C, D, we set A equals alpha plus delta, B equals beta minus I gamma, C equals beta plus I gamma, and D equals alpha minus delta. You can solve for the alpha, beta, gamma, deltas in terms of the A, B, C, Ds. You get alpha is A plus D over 2, beta is B plus C over 2, gamma is I over 2, B minus C, and delta is A minus D over 2. Note that we assumed nothing about this matrix. We didn't assume that it was Hermitian. We didn't assume that it was unitary. We didn't assume that it was real. Any 2x2 matrix with arbitrary complex coefficients can be expressed in terms of a sum of the identity matrix and any of the Pali matrices. And that tells you that this is a completeness relationship for 2x2 matrices in terms of the identity matrix and the Pali matrices. So we often write this in a vector notation. It's just a compact notation where the beta sigma x gamma sigma y plus delta sigma z is written as v dot sigma, where v would be the vector beta gamma delta. All right, so let's get some practice working with these objects. Let's look at the product A dot sigma, B dot sigma. We're going to write it out in terms of its coefficients. A dot sigma is the sum over I, AI sigma I. B dot sigma is the sum over J, BJ sigma J. I move the coefficients AI and BJ off to the left because they're numbers. I can then use my product formula for sigma I, sigma J. It's delta IJ times the identity matrix plus I epsilon IJK times sigma K. That's going to give me A dot B times the identity matrix plus I epsilon IJK AI BJ sigma K. And you notice that that's going to equal A dot B times the identity matrix plus I A cross B dot sigma, because that object there is the vector triple product. I hope you remember that. Now note that if A is parallel to B, that vector triple product is equal to 0, and then A dot sigma multiplied by B dot sigma is just A dot B times the identity matrix. This is a very important identity that is really worth remembering. We're going to use it next to calculate the matrix exponential of Pali matrices. So now we're going to calculate the exponential of I v dot sigma. We're going to write that as a power series, sum n equals 0 to infinity, I to the n divided by n factorial multiplied by v dot sigma to the n. Now, we're going to separate out the even and odd powers. So we're going to write it as sum n equals 0 to infinity minus 1 to the n divided by 2n factorial v dot sigma to the 2n plus I times the sum n equals 0 to infinity minus 1 to the n divided by 2n plus 1 factorial v dot sigma raised to the 2n plus 1 power. Now you need to recall what we just worked out above. V dot sigma times V dot sigma is equal to V squared times the identity matrix because V is parallel to itself. That means that V dot sigma to the 2n is just V squared to the n multiplied by the identity matrix. And V dot sigma to the 2n plus 1 is just equal to V dot sigma times V squared raised to the nth power. Now you can see that first summation is the power series for the cosine of the absolute value of V, and that's going to multiply the identity matrix. And that second summation is equal to the sine of the absolute value of V divided by the absolute value of V. To be the sine, I really need that to be absolute value of V raised to the 2n plus 1 power. So I'm going to use a multiply by 1 trick. I'm going to multiply by absolute value of V and divide by absolute value of V. And you see that that summation is equal to sine of absolute value of V divided by absolute value of V. And we get this remarkable identity. And this is a really important identity, gets a big box. E to the I V dot sigma is equal to cosine of V times the identity matrix plus I V dot sigma divided by absolute value of V times sine absolute value of V. All right, let's compute e to the I v dot sigma sigma j e to the minus I v dot sigma. This is called a similarity transformation. We're also going to learn about how to calculate it using something called the Hadamard lemma. That's going to be in a later lecture. But in this case, we can explicitly calculate it because we know what e to the I v dot sigma is. We just use that identity. So e to the I v dot sigma is cosine V times the identity matrix plus I v dot sigma over V times sine v. Remember again, v dot sigma is vx sigma x plus vy sigma y plus vz sigma z. I get my sigma j, and then I get the cosine v times I minus I v dot sigma divided by v times sine of v. Okay, let's work out the product of these different terms. We're just doing a FOIL here. It's a little bit complicated because we have the sigma j factor in the center. But if I look at the first term, it's got a cosine of v squared. I have a I sigma ji, that just is equal to sigma j. The second term is going to be a minus I cosine v sine v divided by v, sigma j times v dot sigma. The third term is going to be a plus I cosine v sine v over v, v dot sigma times sigma j. And then the last term is the sine v terms. That's going to give me plus 1 times sine squared v divided by v squared times v dot sigma sigma j v dot sigma. Okay, let's work out what those products are. I have a sigma j times a v dot sigma. Let's expand out what v dot sigma is as vi sigma I. I have then, you can see that that object in the parentheses is actually a commutator of sigma j with a sigma I, multiplied by that vi and then summed over I. The commutator of sigma j with sigma I is equal to I epsilon ji k summed over k sigma k. So we're going to write that in there. The I is going to cancel with a minus I. And then the last term is going to be a sum over I and a sum over k, vi vk, sigma I, sigma j, sigma k. Remember, we worked out what the triple product was when those three guys were different, but we have to look at all the different cases, so we have to work carefully on that last term. Okay, so let's take a look at that last term. Sum over ik, vi, vk, sigma I, sigma j, sigma k. I'm going to take that first sigma I, sigma j and use that identity we worked out. We're going to write that as delta ij times the identity matrix plus I epsilon ijl sigma L. That has an implicit summation over L in it. When I multiply the identity times sigma k, I just get sigma k. I have a delta ij there. That is going to get rid of the I summation. When I look at the epsilon ijk, ijl sigma L, I have a sigma L times a sigma k. I'm going to replace the sigma L sigma k with our identity again, because that's a product of two Pali matrices. So that's going to give me a delta LK plus an I epsilon LK M sigma M. Now the delta LK term is equal to 0 because you can see that if K is equal to L, I'm going to have a cross product between, I'm going to have a V cross V from that summation over the I and the K, and V cross V is equal to 0. So that delta LK term gives me nothing. I have then a product of these two epsilon IJL, epsilon LKM. When I sum that over L, that's the identity that you should know. It becomes delta IK, delta JM minus delta IM, delta JK. So I then can get rid of a number of additional summations. We look at the first summation. I'm going to set I equals K, sum over that. That's going to give me a V squared. I'm going to set J equals M. That's going to give me a sigma J. The second term is going to set I equals M. That's going to give me a V dot sigma. And then I'm going to set K equals J. That's going to give me a VJ. And so now when all the dust settles, what we get are these contributions. VJ times V dot sigma minus V squared times sigma J plus V dot sigma times VJ. You see that term is appearing twice. We now plug that back into the expressions that we had worked out before. We get cosine squared V times sigma J plus cosine V sine V divided by V, V cross sigma, the jth component, plus sine squared V over V squared, 2 V dot sigma VJ minus V squared sigma J. Okay? That was a lot of work. We might want to take a deep breath here. This could be a good time to pause the video since we've been at it for a while, and then come back for the last part of the lecture. Okay, I hope you're a bit rested. If you didn't need a rest, we're going to just press on. I'm going to now show you something that is something I'm pretty sure you have never seen. It's called exponential disentangling. I want you to first note that sigma plus equals sigma x plus I sigma y. If you go ahead and calculate that, you'll find that that is equal to 0.200. And that means that if I calculate the exponential of alpha times sigma plus, that's 1 plus alpha times sigma plus 1/2 alpha squared times sigma plus squared plus higher order, you can see immediately if you take sigma plus and multiply it by itself, sigma plus squared is equal to 0. And that's enforcing the fact that I can't raise a spin more than once. S plus squared is always equal to 0. And that means that the exponential of this is equal to 1, 2 alpha, 0, 1. Similarly, if I calculate the exponential of alpha times sigma minus, that's equal to, oops, I see a typo there. That should be 1, 0, 2 alpha, 1. Okay. Now, let's consider the following exponential. We're going to want to calculate e to the I v dot sigma. Now, remember, we calculated this because we know what the exponential is. Using our formula and looking at the components of the formula, that is equal to cosine v plus I vz over v sine v, I vx over v plus vy over v times sine v, I vx over v minus vy over v sine v, and cosine v minus I vx over v sine v. Okay, that's just from the exact formula that we worked out. Remember, that was cosine v times the identity plus I v dot sigma divided by v times sine v. All right. Now, what we want to do is we want to rewrite it in a factorized form. E to the alpha sigma plus, e to the beta sigma z, e to the gamma sigma minus. Now, this is a particularly convenient form to write it in, but actually, this identity works no matter what of the 6 different ways that you can pick the factors. So you could pick the sigma plus sigma minus sigma z, you could pick sigma minus sigma z sigma plus, you can pick sigma minus sigma plus sigma z, etc. Any of the 6 possible permutations are valid. We're going to work with this one case that we have here. Okay? So now when we work that out, we just plug in. We already calculate what e to the alpha sigma plus is. It's 1, 2 alpha, 0, 1. Exponential of beta sigma z, that's easy to calculate because it's diagonal. It's just e to the beta, 0, 0, e to the minus beta. Write out the power series and work that out if you're having trouble seeing that. And then I see I have a typo here as well. Exponential of gamma sigma minus is 1, 0, 2 gamma, 1. Now I'm going to multiply the first 2 terms out. You get e to the beta, 2 alpha e to the minus beta, 0 e to the minus beta. We have to multiply that by the second term, and here I have it correctly written with the 1 along both terms of the diagonal. You multiply that out, you get e to the beta plus 4 alpha gamma e to the minus beta, 2 alpha e to the minus beta, 2 gamma e to the minus beta, and e to the minus beta. How do we make this work? We equate the coefficients of the matrix that we got from that multiplication with the matrix that we got by explicitly calculating the exponential. Now I'm going to have to move the page up to put down what that result is, but you just equate these guys. And if you want, it might be a good idea to pause the video and just work out and solve what alpha, beta, and gamma are for calculating the terms that go into this exponential disentangling. If you like, what we're trying to do is we're trying to fit alpha, beta, and gamma given V. All right? So now I'm going to show you what the results are for that by equating the top term. You're going to get cosine V plus I VZ over V sine V equals e to the beta plus 4 alpha gamma e to the minus beta. Looking at the upper diagonal, I Vx over V plus Vy over V sine V is equal to 2 alpha e to the minus beta. You're going to find that I Vx over V minus Vy over V sine V is equal to 2 gamma e to the minus beta. And then looking at the lower diagonal, you get cosine V minus I Vz over V sine V is equal to e to the minus beta. Now, obviously, that last equation is the one I want to solve first. That solves e to the minus beta immediately. The next term, using e to the minus beta, I can plug that into the equation above it and divide by 2 e to the minus beta. That gives me gamma. I can do the same thing with the third equation and get alpha. And then finally, you might ask, okay, I've determined alpha, beta, and gamma. I have no more free parameters, so I have to actually verify that that last equation holds. So let's verify that that last equation holds. Note that e to the beta plus 4 alpha gamma e to the minus beta can be written as e to the beta 1 plus 4 alpha gamma e to the minus 2 beta. Let's plug in. E to the beta is 1 over e to the minus beta, so that's 1 over cosine v minus I vx vz over v sine v, multiplied by 1 plus 4 alpha gamma e to the minus 2 beta. That's just the product of the two middle terms. And that's just equal to sine squared v times vx minus vx squared minus vy squared. You can verify that pretty easily, divided by v squared. Okay. Now I'm going to rationalize the denominator. So I'm going to multiply by 1 in the form of cosine v plus IV z over v sine v divided by cosine v plus IV z over v sine v. The denominator is then going to be cosine squared v plus vz squared over v squared sine squared v. And in the numerator, I get the cosine v plus I vz over v sine v. And now, if you look at the term in the parenthesis, 1 plus sine squared over v, vc squared over v squared minus 1, I simplified that using the fact that v squared is equal to vx squared plus vy squared plus vz squared. So that's an alternative way that I can write minus vx squared minus vy squared over v squared. And now what you see, if I rewrite that, you see I get a 1 minus sine squared v plus sine squared v, vz squared over v squared. But 1 minus sine squared v is just cosine squared v. And you see that that term in the parenthesis is exactly equal to the denominator, so it cancels. And we find that this combination, e to the beta plus 4 alpha gamma e to the minus beta, is equal to cosine v plus I vz over v sine v. But that's what it needed to be in order for this factorization to work. So that means that we've gotten everything to work. So now what I'm going to show you is what you get when you work out explicitly the solution of the bottom three equations. We'd have found e to the minus beta is equal to cosine v minus I vz over v sine v. If I take the logarithm of that and multiply by minus 1, I get beta is minus the logarithm of that linear combination. Notice that's the logarithm of a complex number. You should be familiar with how you take the logarithm of complex numbers. Alpha we solve for by doing that division by the e to the minus beta. And you get the form that's written here. I'm not going to read it out for you. And similarly for gamma. And so we actually now have determined this factorization. Now, a very special case occurs when Vx equals Vz equals 0. Then this simplifies, and you get beta log secant Vy. Alpha is 1/2 tangent Vy, and gamma is minus 1/2 tangent Vy. It turns out this case is a very important case, and we're going to be using that and working with that later in the class quite a few different times. So this is giving you your first taste of exponential disentangling. We're going to learn more about that in the next lecture. With that, we're going to be ending this lecture. Again, I just want to reemphasize for you, what I recommend is that you go through the lecture at regular speed, taking notes, pausing it and taking notes as you need to. It would be good that you actually generate a copy of these notes yourself and add in any of the details or parts that you have a little bit of trouble following. And then I recommend maybe a day or two later that you rewatch the video, probably at 1.25 speed, and make sure that everything makes sense to you. And it's much better to do it that way than rewatching the video immediately afterwards, because if you watch it immediately afterwards, it's just too soon. Your brain hasn't had a time to process it. Now, I also want to say that when I normally teach this class in person, I take 2 hours to do each of the lectures. I hold it in a double lecture session, and we work through them very slowly and carefully, writing everything out on the board. I get the people in the class to help me work through the material and so forth. We can't do this in a remote setting, and that is why it's really important that you follow the instructions that I'm recommending to you, that you watch the video once, taking notes as you work through and working through all of the details, pausing the video and working through some of the things before I tell you how it works, and then a couple days later you rewatch the video. And of course, the video is always available for you. So if you need a refresher at some later date, because we're coming back to a topic that we covered earlier, of course, you can come back and redo the video and rewatch it and figure out again how things work. Okay, until next time, this is Physics 506.